Hi, so I hope this video answers some of your questions about r and r squared. So first we are going to look at our scatter plot. And our scatter plot is going to tell us which metric we will be using to analyze our model. So if our scatter plot looks linear, we are going to use this lowercase r here, which is the Pearson correlation coefficient. This is the equation to calculate it by hand. This kind of walks you through what to do for everything. Then if we have a nonlinear model, so our scatter plot looks like it could be a curve, say quadratic, exponential, sinusoidal, something like that, we would use r squared, the coefficient of determination, in order to measure the goodness of fit of the model to the data. So we are going to use this formula here to calculate capital R squared, or the coefficient of determination. So first I made up some data. So I was like, okay, in a list and spreadsheet, right, I said, okay, so yi is always going to be our actual measurements that we got from real life, okay? So yi are the actuals, and I'm saying maybe this is the height of a ball as time goes on, from 0 to 6 seconds. The ball goes up in the air, the ball reaches its peak, and then the ball falls back down to the ground after 6 seconds. If I were to plot these values on a scatter plot, oh wow, that looks very quadratic indeed. So I would like to generate the equation that would best fit this data, and it looks like it's going to be a downward facing parabola with a vertex at 3, 9. So if I wanted to do downward facing parabola with a vertex at 3, 9, it would look something like this. So this is what would generate my predicted values, right? This is the model that predicts the values. So I would say that this would be x squared minus 6x plus 9 plus 9. I distribute the negative. These cancel, and I would end up with an equation that would look like negative x squared plus 6x. So if I wanted to figure out what the predicted y's would be, I would have to graph this equation and then get a table of values. So 0, 0, 1, 5, 2, 8, 3, 9, 4, 8, 5, 5, and 6, 0. Okay, so these are my predicted values. So I would go into here, and my yi actuals, I think they were 0, 4.6. These were the actual measured ones, so notice how they're not perfect numbers. And this is what I ended up getting. So then these would be my yi hats. These are these predicted values, and they're from the formula that I generated, which is y equals negative x squared plus 6x, okay? So I'm not going to write with an s at the end. It's just yi hat, and then I can write these are the predicteds. The way you can remember that is like, in order to make a prediction, you have to put your thinking hat on. Really darky. Okay, so we got 0, 5, 8, 9. These are just copied from the table after I graphed the equation that I generated based off of the way the data looked. All right, so let's just make our scatter plot. Okay. I don't want it like that. So I've got my scatter plot, and it looks very quadratic indeed. All right, good to know. So now basically what I'm doing is I am generating the equation of the negative x squared minus 6x, or plus 6x, sorry, and I'm kind of plotting it on the same graph here, and then I'm comparing the residual, or the vertical distance, between the actuals and the predicteds, okay? And that's how I measure the goodness of fit of my model. So I'm going back to the equation, and I'm like, okay, so it's the sum of yi minus yi hat. those will be squared, and those will be over the sum of the yi minus y bar, okay? So I'm going to need the y bar here, which is the mean. So y bar is going to be the mean of all the y's. And it's going to look like that. Okay, so I put it in green because I'm going to be using that later. I'm going to need that for the denominator, yi minus y bar. So let's go ahead and calculate that. Yi minus y bar. So yi is the actuals, so that's going to be b4 minus whatever this guy is, b13. Okay, and then this is going to be b5 minus b13. And this is going to be b6 minus b13. Still making a video, children. This is b7 minus b13. And this is going to be b8 minus b13. This is going to be b9 minus b13. And then this is going to be b10 minus b13. So then now what I'm going to do is I'm going to square all these differences here. So I'm going to have this times itself. And then now I'm going to sum all those, and that'll become my denominator there. Okay. And then this is going to be the difference from, or this is like the vertical difference between the actuals and the predicteds from the models. So what I'm going to do is to do, this is the actual, minus the predicted. And then it looks like it's going to start making a suggestion soon. Please suggest the formula. It won't do it. I don't know, sometimes it does. Also, sometimes you can just drag it and it'll suggest it for you, but sometimes it doesn't work for me. So, all right, I'm going to sum all these. Okay, and that was the F column, right? Yeah. Okay, so now what I'm going to want to do here is, according to the formula, I want 1 minus, and then I have the sum squared regression divided by the total sum of squares. And that's going to give me 0.997. Okay, so this is the coefficient of determination for my model that I generated using my knowledge of transformations and the way the data looked. Now let's see what the computer spits out, check his R-squared, and see if we beat the computer or the computer beat us. So let's go ahead and put that on here. Oh, here we go. Sorry, I always forget the order to do this. Alright, I don't want it to be linear. I would like it to be polynomial, second degree polynomial. I would like the label to be the equation, and I would like it to show the R-squared. Okay, so what was the equation that the computer found? Negative pretty close to 1 x squared plus 5.99x pretty close to 6x, and then minus 0.1. We didn't get the minus 0.1, but that's okay. That must be the difference between why their r squared is a little better than our r squared, okay? So hopefully that answers your question about calculating r squared.